Hello there. Come a little closer. Pull the blanket tighter. Let your shoulders drop and let your breath find its own patient rhythm. Because tonight, we are going somewhere that most people never truly visit. Not with their eyes, and certainly not with the quieter parts of themselves. Tonight, we are stepping out of the noise, out of the day's long list of things that matter too much, too loudly, for too many hours. We are stepping into the dark, not an empty dark, not a frightening dark. This is the dark that covers everything, the one that has existed for longer than thought, longer than stone, longer than the first nervous heartbeat of any living thing on this small and tender world. This is the dark between the stars. Above you, right now, whether the sky is visible or not, there is something that staggers the mind and soothes the soul in equal measure. There are galaxies older than anything you have a proper word for. There are stars that have been burning since before the sun was born. Their light still traveling, still moving, still crossing the unthinkable distances between here and somewhere that has no name. There are clouds of gas, so vast and so slowly shifting that they measure their lifetimes in millions of years without once being in a hurry. The universe is not indifferent, it is simply unhurried. And tonight, together we are going to move through it, slowly, with no particular destination. We are going to explore 100 facts about the sky above, about nebulae and black holes, about the scale of space and the strange silence of expansion, about planets no one has ever stood on and stars that burned out before life. Each one is a small door quietly opened. Each one will take you a little further from the noise. You do not need to hold on to anything tonight. You do not need to remember. You only need to listen. 100 facts, one sky, and all the time in the universe. Let's begin. When you look at the Andromeda Galaxy on a clear night, visible to the naked eye as a soft smudge of silver near the constellation Perseus, you are receiving light that left its source approximately 2.5 million years ago. At that time, our ancestors were early hominins, walking the African savanna, not yet fully upright, not yet capable of language or fire. The universe was an entirely different place in its fine details, and yet that light kept traveling without rest, without interruption, across an unimaginable gulf of space, until it reached the lenses of your eyes tonight. It never stopped. It never tired. Photons, once set in motion, travel at the speed of light until something receives them. You are, in this quiet moment, the end point of a 2.5 million-year journey. The light found you after all this time right here. The speed of light, approximately 299,792 kilometers per second, is simultaneously the fastest thing in the known universe, and the reason the universe feels so extraordinarily, humblingly large. Even at that speed, crossing from one side of the Milky Way to the other would take roughly 100,000 years. A signal traveling at the speed of light sent from Earth today would not reach the far edge of our own galaxy until the year 102,000. No human civilization has existed for that long. No written language is even a fraction of that age. And yet the Milky Way is considered, in the grand scheme of things, an unremarkable mid-sized galaxy among an estimated 2 trillion others spread across the observable universe. Distance, at cosmic scales, becomes something the mind cannot fully hold, only quietly accept, like the sound of rain on a distant roof. Stars do not twinkle. From space, A star is a steady, unwavering point of light, perfectly stable, burning with extraordinary consistency. What we see as twinkling from the ground is entirely an effect of Earth's atmosphere. As starlight passes through layers of air at different temperatures and densities, it is refracted, bent and scattered, many times per second. The result is that rapid, shimmering flicker that poets have described since the beginning of written language. Planets, by contrast, appear as disks rather than points even at great distances, and the multiple light paths from a disk tend to average out the atmospheric interference. This is why planets appear steadier in the sky than stars. The twinkling is not the star's voice. It is Earth's atmosphere whispering softly as the light passes through on its long way down to you. The Sun is so large that approximately 1.3 million Earths could fit inside it, and yet it is considered a relatively ordinary, medium-sized star. It belongs to a classification called G-type main sequence stars, sometimes called yellow dwarfs. Though the Sun appears white from space, not yellow, our Sun is thought to be about 4.6 billion years old, currently in the middle of its life cycle, and it is expected to continue burning in roughly its present form for another 5 billion years. It converts approximately 600 million metric tons of hydrogen into helium every single second through nuclear fusion, releasing energy that takes anywhere from 10,000 to 100,000 years to migrate from the core to the surface before making the final 8-minute journey to Earth as visible light and warmth. There exists a class of stars called red supergiants that are so extraordinarily large that the concept of size bends the imagination until it nearly breaks. Betelgeuse, the reddish star in the shoulder of Orion, has a radius between 700 and 1,000 times larger than our Sun. If Betelgeuse were placed at the center of our solar system, its surface would extend roughly to the orbit of Jupiter, swallowing Mercury, Venus, Earth, and Mars entirely. Betelgeuse is also what astronomers classify as a pre-supernova candidate. At some point, perhaps within the next 100,000 years, it will exhaust its fuel and collapse before exploding in a supernova so bright it may be visible in daytime from Earth. A star it has been, burning for millions of years. A quiet giant, resting in the winter sky above you. The color of a star tells you its temperature with remarkable precision. The coolest stars, those with surface temperatures of around 3,000 degrees Celsius, glow a deep, rich red. As surface temperature rises, stars progress through orange, then yellow, then the brilliant white of stars around 10,000 degrees, and finally into the blue-white of the hottest stellar bodies, which can reach surface temperatures of 40,000 degrees or more. Our own Sun sits comfortably in the yellow-white range, with a surface temperature of roughly 5,500 degrees Celsius, though its corona, the outermost atmospheric layer, paradoxically reaches temperatures of 1 to 3 million degrees, a puzzle that solar physicists are still quietly working through. The night sky is not uniformly white. It is a color chart of physics, arranged casually across the dark, for anyone patient enough to look. Something extraordinary happens inside the core of a dying star at the moment it can no longer sustain nuclear fusion. For most of a star's life, the outward pressure of the energy generated by fusion precisely counterbalances the inward pull of its own gravity. A delicate and ongoing equilibrium. When the fuel runs out, that balance collapses. Gravity wins, suddenly and completely, within a fraction of a second. The core of a massive star can implode, compressing the equivalent of several solar masses into a volume roughly the size of a city. This catastrophic collapse releases more energy in a fraction of a second than the Sun will emit over its entire 10 billion year lifetime. The resulting explosion, a core collapse supernova, scatters the star's outer layers across light years of space, seeding future solar systems with the heavier elements that eventually become planets, oceans, and the iron in your blood. There is a star catalogued as Epsilon Aurigae that astronomers have been puzzling over for more than 2 centuries, every 27 years. This extraordinary system dims significantly for a period of roughly 2 years, a dimming so pronounced and so long-lasting that it clearly indicates something enormous is passing in front of it. The leading current explanation is that Epsilon Aurigae is a binary system, and its companion is surrounded by a vast, opaque disk of dust and gas that periodically eclipses the primary star from Earth's line of sight. That the disk appears to have a dark band running through its center, suggesting a forming planet system hidden within it. A star that astronomers have been quietly watching for over 200 years. Some wonders are not solved quickly. Some are simply companionable mysteries, like an old book you keep returning to. The oldest known star currently catalogued, HD 140283, sometimes called the Methuselah star, is estimated to be approximately 14.5 billion years old, with a margin of uncertainty of around 800 million years old. For context, the universe itself is estimated to be 13.8 billion years old. This apparent paradox is resolved when one accounts for the observational uncertainties in both measurements, but it remains one of those delightful reminders that the universe does not always arrange itself neatly for our convenience. 283 sits relatively close to us astronomically speaking, at about 190 light-years away in the constellation Libra. It is a subgiant star, slowly evolving. It formed when the universe was young and metal poor, before the great forges of supernovae had scattered heavier elements widely through space. It has been there, burning through all of recorded human history and immeasurably more before it. Binary star systems, in which 2 stars orbit a common center of gravity, are not the exception in the universe. They may, in fact, be more common than single stars. Roughly half, and possibly more, of all Sun-like stars are thought to exist in binary or multiple star configurations. Some binaries are so close that they nearly touch, completing orbits in hours. Others are so widely separated that a single orbit takes thousands of years. There are even triple, quadruple, and quintuple star systems, each body gently tugging at the others in complex gravitational dances that can remain stable for billions of years. The night sky, seen from many planets in binary systems, would offer a sky with 2 sunrises, 2 shadows, and the strange, layered warmth of 2 distant suns. A sight no human eye has ever witnessed, except in imagination. There is a nebula catalogued as the Boomerang Nebula, located roughly 5,000 light-years from Earth in the constellation Centaurus, that holds an extraordinary distinction. It is the coldest natural place ever measured in the known universe, with a temperature of approximately 1 degree Kelvin, just 1 degree above absolute zero. This is colder than the average background temperature of deep space itself, which sits at around 2.7 degrees Kelvin. The nebula's extraordinary chill is the result of a dying star expelling gas at tremendous speed, approximately 164 kilometers per second, causing the gas to cool as it expands outward, in the same way that a pressurized gas cools as it escapes through a nozzle. Cold as an ancient breath, This small cloud of gas holds a temperature that the emptiest parts of space cannot match. A neutron star is what remains after certain types of supernovae, an object of almost impossible density. The average neutron star has a mass between 1 and 2 times that of our Sun, compressed into a sphere roughly 20 kilometers across. A single teaspoon of neutron star material would weigh approximately 4 billion metric tons on Earth. The surface of a neutron star is so smooth, the crushing gravity prohibiting any feature taller than a few centimeters, that it makes the most perfectly machined ball bearing on Earth look jagged by comparison. Some neutron stars rotate hundreds of times per second, emitting beams of electromagnetic radiation from their magnetic poles that sweep across space like cosmic lighthouses. These are called pulsars. Their timing is so precise that they have been seriously proposed as navigation beacons for interstellar spacecraft. Light pollution now affects more than 80% of the world's population, and a startling third of humanity can no longer see the Milky Way from where they live. This is a geologically new problem. For most of human history, the full sweep of our galaxy across the night sky was as familiar a sight as the moon. It shaped mythology, guided navigation, anchored the seasons, and offered a nightly reminder that the world extended far beyond the edges of any campfire or city wall. The quiet rewilding of dark skies has become a growing global movement. There are official dark sky reserves now on every inhabited continent, places deliberately protected from artificial light, so that people can once again stand under a sky unchanged since our species was young. To see the Milky Way with your own eyes is to feel, without needing any explanation, how small and how precious this place is. The boundary of a black hole, the point of no return beyond which nothing can escape, is called the event horizon. It is not a physical surface. There is no wall there, no membrane you could touch. If you were falling toward a black hole from a safe distance, you would cross the event horizon without feeling any particular sensation at the moment of crossing. You would not even know precisely when you had passed it. From the outside, however, an observer watching you fall would see your image slow, redden, and fade, stretched thin by gravitational time dilation until you appeared to freeze at the horizon's edge, your last signal growing dimmer and redder across billions of years. The black hole keeps its secrets behind a curtain that has no texture, no temperature, and no gate. Stephen Hawking's most celebrated contribution to theoretical physics was the prediction that black holes are not entirely silent. Through a quantum mechanical process now called Hawking radiation, black holes slowly emit a faint thermal glow at their edges, not from inside the event horizon, but from the turbulent quantum foam just outside it. Virtual particle pairs that would normally appear and annihilate each other in empty space can, near an event horizon, be separated. One falls in, one escapes. The escaping particle carries away a tiny quantity of energy, over immense timescales, vastly longer than the current age of the universe for all but the smallest black holes. This process causes a black hole to very gradually lose mass and ultimately, theoretically, evaporate entirely. What Hawking radiation leaves behind, and whether information is preserved in the process, remains one of the deepest open questions in physics. Not all black holes are the same size, and the spectrum spans a range almost too large to describe in ordinary language. Stellar mass black holes, formed by the collapse of individual massive stars, typically range from a few to a few dozen solar masses. Intermediate mass black holes, still somewhat mysterious and rarely observed, may contain thousands to hundreds of thousands of solar masses, and at the centers of most large galaxies, including our own, sit supermassive black holes containing millions to billions of solar masses. The supermassive black hole at the center of the Milky Way, designated Sagittarius A, has a mass of approximately 4 million suns, compressed into a region not much larger than our solar system. Despite its mass and its proximity of only about 26,000 light-years, it poses no danger to Earth whatsoever. In April 2019, humanity saw a black hole for the very first time. The Event Horizon Telescope, a planet-spanning network of radio observatories working in concert as a single Earth-sized dish, captured an image of the supermassive black hole at the center of galaxy M87, located approximately 55 million light-years away. The resulting image showed a bright, asymmetrical ring of glowing gas encircling a central dark shadow, the black hole's silhouette against the luminous material swirling around it. This shadow, technically called the photon sphere, was exactly the size that Einstein's general relativity predicted it should be. A century after the theory was published, the image arrived, a dark circle surrounded by light, seen from across 55 million years of space, and it was precisely where the mathematics had promised it would be. Black holes spin. In fact, most astrophysicists believe that the majority of black holes rotate, possibly very rapidly, because the stars that formed them were themselves rotating, and angular momentum is conserved through the collapse. A spinning black hole is described by the Kerr metric in general relativity, and it has a peculiar additional feature, a region outside the event horizon, where space-time itself is dragged along in the direction of rotation, like water caught in a whirlpool. This region is called the ergosphere. Theoretically, it is possible to extract energy from a rotating black hole by dropping matter into the ergosphere in precisely the right way, a process proposed by physicist Roger Penrose. The black hole slows very slightly, and the extracted object emerges with more energy than it carried in. The universe offers strange gifts occasionally to those who approach carefully enough. There is a category of black holes called blazars that happen to be oriented so that one of their relativistic jets, twin beams of plasma and radiation expelled from the poles of the accretion disk, points almost directly toward Earth. When this alignment occurs, the result is a brilliance that can outshine an entire galaxy by a factor of thousands. Blazars are among the most luminous, most energetic, and most variable objects in the known universe, flickering and flaring in ways that can change dramatically over hours or days. Some have been detected at distances of more than 12 billion light-years, meaning we're observing them when the universe was only a fraction of its current age. Their light has traveled longer than Earth has existed, and it arrives here quietly absorbed by our instruments, a message from the very early cosmos. Einstein's general theory of relativity, published in 1915, predicted that massive objects do not simply attract each other across empty space, they warp the fabric of space-time itself, and what we experience as gravity is the curvature of that fabric. One of the strangest consequences of this warping is gravitational lensing. When light from a distant object passes near a massive foreground object, a galaxy cluster, for example, the warped space-time, bends the light's path. The result is that a single distant source can appear as multiple images, arcs, or rings when viewed from Earth. Einstein rings, perfect circular arcs of lensed light, are among the most visually striking confirmation of relativity that the sky offers. The universe, without any human intention, has built natural telescopes from pure gravity, focusing the glow of objects too faint and too distant for any instrument to see unaided. There is a class of objects called quasi-stellar objects, quasars, that are powered by supermassive black holes actively feeding on surrounding matter. In their accretion disks, gas and dust heat to temperatures of millions of degrees, radiating with a brilliance that makes them visible across billions of light years. The most luminous quasars outshine entire galaxies of hundreds of billions of stars. We see quasars predominantly at great distances, meaning great ages, because the epoch of peak black hole feeding activity was billions of years in the past, when the universe was younger and galaxies were richer with fresh gas. Our own Milky Way hosts a supermassive black hole that was almost certainly an active quasar long ago. Today it is quiet, barely stirring, but the evidence of that former ferocity lives on, in the very structure of the galaxy around it. Time slows near a massive gravitational source. This is a prediction of general relativity that is not a metaphor, but a measurable physical reality. Atomic clocks on the surface of the Earth tick slightly slower than identical clocks in orbit because they sit deeper in Earth's gravitational well. GPS satellites must account for this effect in their calculations, without corrections for both special and general relativistic time dilation. The positioning errors would accumulate at a rate of roughly 11 kilometers per day. Near a neutron star or a black hole, the time dilation becomes extreme. An observer hovering just outside the event horizon of a stellar mass black hole for a single hour would return to find that years had passed for those who waited at a safe distance. Time is not a fixed river. Gravity bends it, gently and relentlessly, wherever mass accumulates. In 2015, a century after Einstein published his general theory of relativity, two instruments of extraordinary sensitivity detected something no instrument had ever measured before: a gravitational wave, a ripple in the fabric of space-time itself, caused by the merger of two black holes approximately 1.3 billion light-years away. The wave that reached Earth stretched and compressed the distance between the detectors by less than 1,000th the diameter of a proton. The instruments at LIGO, the Laser Interferometer Gravitational Wave Observatory, presentative enough. The signal lasted a fraction of a second. In that brief shudder, 1.3 billion years of travel reached its conclusion. Since then, dozens of gravitational wave events have been catalogued. Black hole mergers, neutron-star collisions, each one a ripple in space-time arriving from an extraordinary distance, like a sound heard through a wall of inconceivable thickness. There is a curious theoretical possibility, consistent with general relativity, that a sufficiently large and non-rotating black hole might contain at its center not a physical singularity, a point of infinite density, but something stranger. Some models suggest that once you pass the event horizon of a supermassive black hole, the tidal forces near the center might be mild enough for hypothetically extended survival, at least briefly. You would not be crushed at the moment of crossing. What waits deeper in, at the singularity where physics as we understand it breaks down entirely, remains unknown and perhaps unknowable by any external observer. Every calculation that approaches that point reaches a place where our current theories stop producing meaningful answers. The singularity is not just a mystery. It is the precise location where our best descriptions of reality quietly admit they have reached their limit. Black holes can form in ways other than stellar collapse. In the early universe, within the first second after the Big Bang, conditions of extreme density may have given rise to primordial black holes. formed not from dying stars, but from the direct collapse of overdense regions of the primordial plasma itself. These hypothetical objects could range from microscopic to enormous. Some physicists have proposed that dark matter, the invisible substance that appears to make up roughly 27% of the universe's total energy content but has never been directly observed, might be composed partly or entirely of primordial black holes. This remains unconfirmed, but it is an elegant possibility that the mystery we call dark matter is not some exotic new particle, but simply very old, very small black holes left over from the universe's first chaotic moments, silent, cold, invisible, and everywhere the very concept of a black hole, an object so massive that light could not escape it, was first proposed not by Einstein but by an 18th century English clergyman and natural philosopher named John Michell in a paper submitted to the Royal Society in 1783. Michell calculated that a sufficiently massive star, what he called a dark star, would have an escape velocity exceeding the speed of light, making it invisible in principle. French mathematician Pierre-Simon Laplace arrived independently at the same conclusion a few years later. Both men were working purely from Newtonian mechanics, without any concept of space-time curvature or relativity, and yet they arrived at a destination that modern physics has confirmed in extraordinary detail. Some ideas find their way into the world long before the mathematics to fully describe them exist. The intuition arrives first, patient and quiet, waiting for the proof. The Orion Nebula is one of the most studied objects in the sky and one of the few nebulae visible to the naked eye. Located roughly 1,344 light-years away in the sword of the constellation Orion, it is an active stellar nursery, a region of dense gas and dust within which stars are forming right now, at this very moment, as you lie still, and the planet turns. The nebula stretches across a region roughly 24 light-years in diameter and contains thousands of young stars in various stages of early development. Many of these young stars are surrounded by protoplanetary disks, flat rotating regions of gas and dust that may, over the next several million years, coalesce into planets. The Orion Nebula is not a still life. It is a process, patient and ongoing, visible from Earth with nothing more than a clear sky and steady eyes. The Pillars of Creation, a region within the Eagle Nebula, photographed famously by the Hubble Space Telescope in 1995, are towering columns of cold interstellar gas and dust, each several light-years tall, within which new stars are assembling themselves from the surrounding material. The columns are being slowly eroded by the ultraviolet radiation, blasting outward from nearby young, hot stars. But the erosion is slow enough that dense knots of gas within the columns, called EGs, or evaporating gaseous globules, may still collapse and ignite into stars before the columns are fully dispersed. There is a particular poignancy to the pillars. Infrared observations suggest that a nearby supernova blast wave may already have destroyed those columns entirely since the light we see left them. We may be looking at something that no longer exists, a monument to stellar birth, beautiful and already gone. Not all nebulae glow by their own light. Reflection nebulae are clouds of dust and gas that do not emit light themselves, but instead scatter the light of nearby stars, the way a thin fog around a street lamp glows not from its own energy but from the light it redirects. Reflection nebulae tend to appear blue for the same reason. The sky is blue. Shorter wavelengths of light are scattered more efficiently than longer ones, so blue light is preferentially reflected in all directions while redder light passes through. The Pleiades star cluster, one of the most recognizable and beloved star groupings in the northern sky, is embedded in a faint reflection nebula that gives its brightest stars a delicate, misty halo in long-exposure photographs. Stars surrounded by their own soft fog. It is a sight that feels, somehow, like a memory of very early things. Dark nebulae are clouds of gas and dust so dense that they block the light of everything behind them, appearing in the sky not as glowing structures, but as silences, patches where the stars simply stop. The Horsehead Nebula in Orion is perhaps the most famous example. A dark pillar of dense gas rising against a bright red backdrop of ionized hydrogen, its outline resembling from our particular angle the profile of a horse's head. Dark nebulae are not necessarily quiet in their interiors. Many are active regions of star formation, the density that blocks visible light being precisely the same density that gravity needs to begin pulling gas into collapsing cores. The darkness is productive. It is a kind of incubation, thick, opaque, and full of potential for light that has not yet arrived at its ignition point. The Tarantula Nebula, located in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, is the most luminous and active star-forming region known in the local group of galaxies. It contains thousands of young, massive, intensely hot stars, including some of the most massive individual stars ever observed. If the Tarantula Nebula were located at the same distance from Earth as the Orion Nebula, it would cast visible shadows on the ground at night. Its most spectacular feature is a compact cluster of stars called R136 at its core, which contains several stars exceeding 150 times the mass of our Sun, near the theoretical upper limit for how massive a single star can become before radiation pressure tears it apart. The tarantula is the universe at its most productive and most extravagant, making stars the way rivers make sound, constantly, without particular intention, as a natural consequence of conditions. Emission nebulae glow because the gas within them is ionized, stripped of electrons by the intense ultraviolet radiation from nearby young hot stars. When electrons recombine with ions, they emit light at specific wavelength corresponding to particular atomic transitions. The vivid red of many nebulae in photographs corresponds to the H-alpha emission line of hydrogen. Light emitted when an electron drops from the third to the second energy level of a hydrogen atom. The blues and greens visible in other nebulae correspond to emissions from oxygen and other elements. These emission lines act like a chemical signature, allowing astronomers to determine the composition of a nebula from its spectrum alone. The colors are real, though the full visual depth of most nebulae lies beyond what the unaided human eye can register. Long-exposure photography reveals a palette written in atomic physics, glowing patiently across the light years. Some nebulae stretch so large that the mind resists processing their scale. The Tarantula Nebula is roughly 1,000 light-years across. The Carina Nebula, a region of intense star formation visible from the southern hemisphere, is approximately 300 light-years in diameter. But the largest known nebula is the Taffy Galaxy's interacting system, and in terms of pure diffuse gas clouds, structures like the California Nebula or the expansive supernova remnant GSH 1380194, stretching over 1,000 light-years across, remind us that the space between stars is not as empty as it first appears. It is instead threaded with structure, filaments, loops, bubbles and arcs of gas left behind by generations of stars that lived, radiated, exploded, and dissolved back into the medium from which the next generation will eventually gather itself. Stars do not form alone. When a region of a nebula collapses, it rarely produces a single star in isolation. Instead, the collapsing cloud tends to fragment as it spins, producing clusters of stars, sometimes dozens, sometimes thousands, all born from the same parental cloud at roughly the same time, and initially still wrapped together within the remnants of the cloud from which they came. Over millions of years, these star clusters can be dispersed by gravitational interactions with other stars and clouds. But their origin in common material means that stars born together share similar compositions, similar ages, and similar initial conditions. By studying star clusters, open clusters like the Hyades or the Pleiades, or globular clusters like Omega Centauri, astronomers can essentially observe how different masses of stars age, all variables held roughly constant. There is a stage in a young star's development called the T-Tauri phase, named after the prototype T-Tauri star in the constellation Taurus, during which the star is generating energy not yet from nuclear fusion but from gravitational contraction, slowly shrinking and converting gravitational potential energy into heat and light. T-Tauri stars are typically surrounded by disks of gas and dust, and they emit powerful stellar winds and jets of material along their rotation axis. These jets, called Herbig-Haro objects, when they collide with surrounding gas and light it up, are among the most beautiful transient structures in the sky, bright curved arcs glowing where supersonic outflow meets the quiet of the surrounding nebula. A star learning to be a star, sending out its first strong breaths into the cloud that made it. These are the very first pages of a stellar biography. The space between stars is not truly empty. What astronomers call the interstellar medium, the gas and dust occupying the space between stellar systems within a galaxy, is extraordinarily thin by any laboratory standard, with average densities of roughly 1 atom per cubic centimeter. And yet across the vast distances of a galaxy, this tenuous material amounts to a significant mass and plays a crucial role in the galaxy's life cycle. Supernovae stir and heat it. Stellar winds compress and sculpt it. Gravity slowly draws it back together in new condensations. The interstellar medium cycles matter through the galaxy, from stellar birth to stellar death, from explosion back to cloud, from cloud to star again, in a process of cosmic recycling that has been running without interruption since the earliest galaxies formed. Nothing is truly lost. It simply changes shape and waits. The molecular clouds from which stars form contain not just hydrogen and helium, but a surprising complexity of organic molecules. Radio telescopes have detected more than 200 distinct molecular species in interstellar space, including formaldehyde, ethanol, glycine, a simple amino acid, one of the building blocks of proteins, and even polycyclic aromatic hydrocarbons, complex ring-shaped carbon compounds. The interstellar medium appears to be a kind of distributed chemistry laboratory where molecules form on the surface of dust grains, sheltered from ultraviolet radiation in the dense hearts of molecular clouds. When these clouds collapse into new solar systems, some of that chemistry is inherited by the forming planets and their surfaces. Life on Earth may carry, in its most fundamental molecules, the chemical inheritance of the interstellar cloud that became our solar system. A connection between biology and the space between stars that grows more interesting the more carefully it is examined. The Milky Way, our home galaxy, is a barred spiral galaxy. approximately 100,000 light-years in diameter, though more recent measurements of its outer reaches suggest it may extend as far as 200,000 light-years, when its sparse outer disk is included. Our solar system sits roughly 26,000 light-years from the galactic center, within a minor spiral arm called the Orion Arm or the Local Arm. The Milky Way contains between 100 and 400 billion stars and is estimated to harbor at least as many planets, possibly far more. Its central bar structure is thought to help channel gas toward the inner galaxy, feeding ongoing star formation. The entire disk rotates, but not like a solid wheel. Each star follows its own orbit, and the outer regions rotate more slowly than a rigid body would, a pattern consistent with a massive invisible halo of dark matter surrounding and permeating the galaxy. The Milky Way is not alone. It sits at the center of the local group, a gravitationally bound collection of more than 50 galaxies spread across a region roughly 10 million light-years across. The two most prominent members, after the Milky Way, are the Andromeda Galaxy, M31, and the Triangulum Galaxy, M33. Dozens of smaller dwarf galaxies orbit both the Milky Way and Andromeda like moons around planets, some so diffuse and faint that they were only discovered in recent years through digital sky surveys. The large and small Magellanic Clouds, visible in the southern hemisphere as detached patches of the Milky Way, are two of these dwarf companions, actively interacting with our galaxy's gravitational field. The local group is not a fixed arrangement. It is a slow, gravitationally choreographed drift of dozens of galaxies, all drawing gently closer over billions of years. The Andromeda Galaxy and the Milky Way are on a collision course. In approximately 4.5 billion years, the two galaxies will begin to merge, a process that will unfold over hundreds of millions of years, not in any sudden catastrophic event. Despite the spectacular imagery the word collision suggests, the actual experience would be anticlimactic in terms of direct star-to-star impacts. The distances between individual stars are so enormous that no two stars are statistically likely to collide. What will happen instead is a gravitational restructuring. Tidal forces pulling long streamers of stars from each galaxy, the spiral arms distorting and interweaving, the two central black holes spiraling toward each other over immense time before eventually merging. The result will be a new, larger, irregular or elliptical galaxy, already nicknamed Milkomeda by astronomers, utterly unlike either of its parent galaxies in structure. Beyond the local group, galaxies gather into larger structures called clusters, and clusters gather into superclusters. The local group is itself part of the Virgo supercluster, a vast flattened structure roughly 110 million light-years across, containing dozens of galaxy groups and smaller clusters along a filamentary arrangement centered on the Virgo cluster, a dense concentration of roughly 1,500 galaxies. In 2014, astronomers remapped the boundaries of the supercluster using galactic velocity data and identified an even larger structure, of which the Virgo supercluster is merely a small peripheral region. The Laniakea supercluster is merely a small peripheral region. The Laniakea supercluster, spanning approximately 520 million light-years and containing the mass of 100 million billion suns. The name Laniakea comes from the Hawaiian for immeasurable heaven. It is a fitting name. To call it large is to use a word built for smaller things, pressed into service beyond its proper range. On the very largest scales, the universe reveals a structure that no one anticipated before the era of large-scale galaxy surveys, what cosmologists call the cosmic web. Galaxies and galaxy clusters are not distributed randomly through space. They are arranged along filaments, long thread-like structures of dark matter and baryonic matter that intersect at nodes where the densest galaxy clusters sit, separated by vast, largely empty regions called voids. This filamentary architecture emerged from tiny quantum fluctuations in the density of the early universe, amplified over 13.8 billion years of gravitational attraction. Simulations of cosmic structure formation, run on some of the world's most powerful computers, reproduce these filaments with remarkable accuracy. The universe, at its largest scale, resembles a three-dimensional web of extraordinary complexity, and remarkably, it also resembles the neural networks of the human brain. A coincidence that has fascinated physicists and neuroscientists in equal measure. The observable universe has a radius of approximately 46.5 billion light-years. This figure surprises many people, since the universe is only 13.8 billion years old and light travels at a finite speed. The apparent discrepancy arises because the universe has been expanding throughout its history. Regions that were once close enough for light to reach us have been carried further away by the expansion of space itself. The most distant light we can observe, the cosmic microwave background radiation, was emitted roughly 380,000 years after the Big Bang from a surface of last scattering that has since been carried to its current distance by cosmic expansion. What lies beyond the observable universe is simply unknown, not because space ends there, but because the light from those regions has not yet had time to reach us. The universe, in all likelihood, extends far beyond what we can see, perhaps infinitely far. Galaxy morphology, the shape of galaxies, tells a story about their histories. Spiral galaxies like the Milky Way and Andromeda have active star formation ongoing in their arms, where gas and dust are compressed into new stellar generations. Elliptical galaxies, smooth, featureless, shaped like footballs or spheres, are generally made of older stars, have exhausted most of their star-forming gas, and are thought to have resulted from mergers of earlier spiral or irregular galaxies. Irregular galaxies, as the name suggests, have no obvious regular structure and often show signs of gravitational disturbance or interaction with neighbors. Lenticular galaxies sit between spirals and ellipticals, disc-shaped but lacking prominent spiral arms. Each of these shapes is not merely aesthetic. It is a biography written in stellar distribution, the accumulated record of every interaction, merger, burst of star formation, and gravitational encounter the galaxy has experienced across billions of years. The Virgo cluster, the nearest large galaxy cluster to the Milky Way, at approximately 53 million light-years away, contains somewhere between 1,300 and 2,000 galaxies of various types, spirals, ellipticals, lenticulars, all gravitationally bound together in a loose, slowly evolving community. At its heart sits M87, the giant elliptical galaxy, whose central black hole was the first ever imaged directly. The cluster's gravitational influence extends so broadly that it is actually drawing the entire local group, including the Milky Way slowly toward it in a drift of roughly 200 kilometers per second, known as the Great Attractor Flow. Though the Milky Way will never actually fall into the Virgo cluster, the acceleration of the universe's expansion works against such long-range infoul. The gravitational whispering of that distant, dense region shapes the motion of our galaxy in ways that were only mapped in detail in the latter decades of the 20th century. The galaxies we observe at very large distances are not the same as nearby galaxies. They are younger versions of galaxies, seen as they were when the universe was a fraction of its current age. This imposes an extraordinary constraint and an extraordinary gift on astronomy simultaneously. We cannot see what distant galaxies look like today, but we can watch how galaxy populations evolve over cosmic time. Observing galaxies at progressively greater distances effectively means looking at progressively younger epochs of the universe. Deep field images, long exposures of tiny, dark patches of sky, reveal thousands of galaxies at various distances and ages in a single frame, providing a cross-section of galactic history. The Hubble Ultra Deep Field, for example, shows galaxies as they appeared when the universe was less than 1 billion years old, some of them small and irregular, not yet settled into the grand spiral forms we associate with mature galaxies. Not all galaxies are stable, long-lived structures. Dwarf spheroidal galaxies, the most common galaxy type in the universe, are small, diffuse, and contain very little gas or active star formation. Many of them are ancient relics. Their stars formed in the early universe and have not been refreshed since, leaving the galaxy to age slowly without renewal. Some dwarf galaxies that orbit larger galaxies like the Milky Way are being actively disrupted by tidal forces, stretched into long stellar streams that will eventually be incorporated entirely into the larger galaxy's halo. The Sagittarius dwarf spheroidal galaxy, for instance, is currently being torn apart by the Milky Way's gravity and is leaving a long arc of stars wrapped around the galaxy, a stellar stream that traces the orbit of the dwarf's final passage. Galaxies, like everything else in the universe, are not permanent. They evolve, merge, and are absorbed. The spaces between galaxies, the intergalactic medium, are the most extreme voids in the observable universe, and yet they are not entirely empty. A very sparse distribution of hot, ionized hydrogen plasma threads through the space between galaxy clusters, sometimes called the warm-hot intergalactic medium. This gas is so diffuse, less than 1 particle per cubic meter, that it is essentially invisible to most instruments, but models suggest it may contain more ordinary baryonic matter than all the stars and galaxies in the universe combined. The gas is heated to temperatures of hundreds of thousands to millions of degrees by the shock waves of cosmic structure formation. The collision of infalling material along the cosmic web's filaments in the vast, dark spaces between galaxies, where no star has ever burned and no planet could survive, there is still matter, still motion, still a faint, warm presence, connecting everything to everything else. Our understanding of the universe's large-scale structure underwent a quiet revolution in the late 1990s with the discovery that the expansion of the universe is not slowing down, as gravity would suggest, but accelerating. 2 independent teams of astronomers, observing Type Ia supernovae as standard candles to measure cosmic distances, both found that distant supernovae were fainter than expected, meaning they were farther away than they should have been if the universe's expansion rate had been decelerating under the pull of gravity. Something is driving the expansion faster over time. This something has been named dark energy, and it appears to constitute roughly 68% of the total energy content of the universe, the single largest component, and yet nothing about it is directly understood. Its nature is the deepest open question in cosmology. The universe is being pushed apart by something we cannot see, cannot explain. The cosmic microwave background, a faint glow of microwave radiation filling the sky uniformly in every direction, is the oldest light in the universe. It was released approximately 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into neutral hydrogen for the first time, allowing photons to travel freely for the first time without being immediately scattered. Before this, the universe was opaque, a glowing plasma through which light could not travel. The cosmic background represents the moment the universe became transparent. It has been traveling ever since, filling all of space, cooling as the universe expands, stretched from visible light to microwave by the expansion of space-time itself. To detect it is to hear the echo of the universe's earliest accessible moment, a whisper that has been traveling for 13.8 billion years, arriving gently in every direction, all at once. The first confirmed detection of a planet orbiting a sun-like star came in 1995, when Michel Mayor and Didier Queloz announced the discovery of 51 Pegasi b, a planet roughly half the mass of Jupiter, orbiting its host star at a distance so close that its year lasts only 4.2 Earth days. The planet's surface temperature is estimated at over 1,000 degrees Celsius, and it is tidally locked, meaning one hemisphere permanently faces its star in perpetual blazing day, while the other faces eternal night. Before this discovery, most astronomers assumed that gas giants could only form far from their host stars, where it is cold enough for ices and gases to accumulate, and yet here was one hugging its star at a fraction of Mercury's distance from the Sun. Mayor and Queloz were awarded the Nobel Prize in Physics in 2019. 51 Pegasi b changed everything that astronomers thought. They knew about how solar systems are arranged. Hot Jupiters, gas giants orbiting extremely close to their host stars, were the first exoplanet type discovered in large numbers, partly because their combination of large mass and short orbital period makes them the easiest to detect using the radial velocity method. But they are now understood to be relatively rare, accounting for less than 1% of all planetary systems. Their existence presents a puzzle. Gas giants almost certainly cannot form so close to a star, where the disk of material is too hot and too thin. The leading explanation is planetary migration, the idea that these worlds formed much farther out and then spiraled inward over millions of years through gravitational interactions with the protoplanetary disk or with other planets. The migration stranded them close to the star, where the disk eventually dissipated and could no longer pull them further. They have been circling their stars at that scorching distance ever since, year after year, each year lasting only a matter of days. Among the most fascinating objects in exoplanet science are rogue planets, worlds that drift through the galaxy without any host star, unlit by any sun, wandering the interstellar dark in perpetual cold night. These planets are not science fiction. Gravitational microlensing surveys suggest that rogue planets may be extraordinarily common, possibly outnumbering stars in the galaxy. They were likely ejected from their home solar systems early in their formation history, flung outward by gravitational interactions with other planets or their host star before they could settle into a stable orbit. Some may retain thick atmospheres of hydrogen that act as insulating blankets, trapping residual internal heat from their formation and maintaining subsurface conditions that in the most speculative scenarios might allow for liquid water deep beneath a frozen surface. Wandering worlds, drifting through the dark, unknown and unnumbered. The galaxy is crowded with things that no light touches. There is a planet called WASP-76b orbiting its host star at a distance of only about 4% of the Earth-Sun distance, where the permanent day side reaches temperatures of approximately 2,400 degrees Celsius, hot enough to vaporize iron. During the day, iron evaporates from the surface and low atmosphere into a gaseous form, carried by powerful winds to the planet's much cooler night side, where temperatures drop by roughly 1,000 degrees. The iron vapor condenses and falls as rain. Iron rain. Across the terminator, the boundary between the eternal day and the eternal night, clouds of liquid iron droplets form in the atmosphere and precipitate downward. WASP-76b is tidally locked, so this cycle of iron vaporization and condensation is permanent. An unending iron weather system driven by a temperature difference between two hemispheres that never changes, maintained forever by the star's unblinking proximity. The TRAPPIST-1 system, discovered in full in 2017, caused a quiet revolution in the search for potentially habitable exoplanets. Around a cool, dim red dwarf star roughly 40 light-years from Earth, 7 Earth-sized planets orbit in tightly packed, resonant orbits, and 3 of them sit within the star's habitable zone, where liquid water could theoretically exist on their surfaces given suitable atmospheric conditions. TRAPPIST. One is so dim and so cool that its habitable zone sits much closer than the Sun's. One of the habitable zone planets completes an orbit in just 12 days. All 7 planets are tidally locked to varying degrees. The system has become a reference point in discussions of where life might exist beyond Earth, and remains one of the primary targets of the James Webb Space Telescope's atmospheric characterization program, as scientists attempt to determine whether any of these 7 worlds hold air, water, or chemistry worth examining more closely. HD 189 733b is a hot Jupiter famous for being one of the most thoroughly characterized exoplanet atmospheres in the catalogue, and for having a color. Direct photometric observations suggest this world is likely a deep cobalt blue. Not from water, as Earth's blue comes from oceans and sky, but from silicate particles in its atmosphere that scatter blue light efficiently, similar in principle to why Earth's sky is blue. The planet's atmosphere contains water vapor, methane, carbon dioxide, and swirling clouds of silicate dust, glass particles, essentially suspended in winds that exceed 8,700 kilometers per hour. It orbits its host star every 2.2 days at a distance of just 5 million kilometers. And it is blue, a detail that carries, in the context of all the strangeness surrounding it, a strange and unexpected familiarity, like meeting the color of Earth on a world where nothing else resembles home. The James Webb Space Telescope, launched on Christmas Day 2021 and reaching its operational orbit at the L2 Lagrange point, 1.5 million kilometers from Earth, in early 2020 represents the most powerful infrared telescope ever built. Among its primary scientific objectives is the atmospheric characterization of exoplanets, particularly rocky, potentially habitable worlds. By observing the spectrum of a star's light, filtered through a planet's atmosphere, during a transit, as the planet passes in front of the star, JWST can identify the chemical fingerprints of atmospheric gases. It has already detected carbon dioxide, water vapor, methane, and carbon monoxide in various exoplanet atmospheres, with an unprecedented level of clarity. The detection of certain combinations of gases, oxygen and methane simultaneously, for example, in a rocky world's atmosphere, could constitute the first credible biosignature ever observed beyond Earth. JWST is looking for that signal quietly, patiently, one transit at a time. Pulsar planets are among the strangest corners of the exoplanet catalogue. In 1992, Alexander Wolszczan and Dale Frail announced the discovery of planets orbiting a millisecond pulsar, a rapidly rotating neutron star designated PSR 1257+12. These were, in fact, the very first exoplanets. They orbit the remnant of a star that died in a supernova, which means they either survived the explosion, an extraordinary scenario, or formed afterward from material in the post-supernova disk. These worlds are lit not by ordinary sunlight, but by the electromagnetic radiation sweeping from the pulsar's poles with each rotation. Any surface on these planets would be bathed in intense radiation. They are silent worlds orbiting a dead star that ticks like a cosmic clock. The first planets humanity ever confirmed beyond our solar system were nothing like anything anyone had imagined a habitable world might look like. The detection method known as direct imaging, capturing actual photographs of exoplanets distinct from their host stars, remains the most technically demanding approach to exoplanet science. But it has produced some remarkable results, because planets are so much fainter than the stars they orbit. Blocking the star's light with a device called a coronagraph is essential. Several directly imaged planetary systems have been captured, including the HR 8799 system, a young star with at least 4 gas giant companions, whose orbital motion has been captured in a series of images taken over several years, producing, when combined, the first genuine movie of exoplanets orbiting another star. Watching those 4 points of light trace their slow arcs is an experience that does something to the sense of scale that no description quite prepares you for. Other worlds moving, other suns attended. The universe does not repeat itself, but it clearly has patterns. Atmospheric escape is a process that shapes the long-term fate of many exoplanets orbiting close to their host stars. When a planet receives intense radiation from its star, the upper atmosphere heats to the point where individual gas molecules gain enough energy to escape the planet's gravity entirely, a process called photoevaporation over geological timescales. This can strip away an entire hydrogen-helium envelope, transforming what was once a mini Neptune into a bare, rocky world. Astronomers have identified what appears to be a deficit of planets at certain radii, a gap in the size distribution of observed planets at around 1.5 to 2.0 Earth radii, which may be precisely the scar left by atmospheric escape, where the original population of small gas-rich planets has been gradually eroded to their rocky cores. The atmosphere does not disappear all at once. It is taken molecule by molecule by the patient fire of the nearby star. There are planets in binary star systems, and the sky above them would look nothing like what we know. Planets orbiting 2 stars are called circumbinary planets, and the first confirmed example, Kepler 16b, was discovered in 2011. It orbits both stars of its binary pair in roughly 229 days, and from its surface, if it had a solid surface, which it does not, being a gas giant, both stars would be visible simultaneously at certain points in its orbit, casting double shadows across the landscape. Casting double shadows across the landscape. Casting double shadows across the landscape. In systems with closely spaced binary stars, the combined gravitational field can still maintain stable planetary orbits. The experience of time on such a world would be strange. Two suns rising at different rates, setting at different times, casting a shifting tane's layered quality of light that no human being has ever stood in and no poet from our world has ever attempted to describe, because no human language has the words built yet for sunsets that arrive in pairs. The earliest unambiguous astronomical records in human history come from ancient Mesopotamia, from the civilizations of Sumer, Akka, Babylon, and Assyria, occupying the fertile region between the Tigris and Euphrates rivers in what is now Iraq. Babylonian astronomers, working from roughly 1800 BCE onward, maintained systematic records of celestial observations on clay tablets in cuneiform script. They identified the periodicity of Venus with remarkable precision, tracked the lunar cycle to a degree of accuracy that their system of arithmetic, which had no concept of infinity or irrational numbers, barely hindered and developed the Saros cycle, the 18-year 1-1 tenor day period after which eclipses repeat in a predictable sequence. The Babylonian astronomical tradition influenced Greek astronomy directly, and through the Greeks, the entire subsequent tradition of Western science. The tablets are still being studied. They contained, in compressed cuneiform columns, nearly 3,000 years of careful observation. Ancient Egyptian civilization oriented itself by the stars in ways both practical and deeply spiritual. The Great Pyramid of Giza, built around 2560 BCE, is aligned with extraordinary precision to the 4 cardinal points, and its internal shafts appear to have been oriented toward specific stars visible from the construction site during that era, including Orion's belt and the fen pole star Thuban in the constellation Draco. The moment each year when Sirius first becomes visible on the eastern horizon just before sunrise as a celestial calendar event of the highest importance, because it reliably heralded the annual flooding of the Nile, which fertilized the farmland of the entire civilization. A single star rising at a particular angle predicted the condition of an entire country's food supply. This is the kind of practical urgency that sharpens observation to a very fine edge across many generations. The Greek astronomer Hipparchus, working in the 2nd century BCE, produced what is considered the first known star catalogue, listing the positions and approximate brightnesses of roughly 850 stars and classifying them on a magnitude scale, from 1 to 6, that, with modifications, is still used today. He also discovered the precession of the equinoxes, the slow wobble of Earth's rotational axis that causes the celestial poles to trace a circular path over a period of approximately 26,000 years, meaning that the pole star changes over time. He discovered this by comparing his own observations with Babylonian records made 2 centuries earlier and noticing that the positions of stars relative to the equinoxes had shifted. Hipparchus worked with no instruments beyond basic sighting tools, and yet he identified one of the most subtle and long-period motions in Earth's behavior. Patiently assembled from the comparison of records separated by 200 years, Claudius Ptolemy's Almagest, written around 150 CE, was the foundational text of professional astronomy for over 1,400 years. In it, Ptolemy synthesized the accumulated Greek astronomical tradition into a coherent mathematical model of the heavens, one that placed the Earth at the center of the universe, with the sun, moon, planets, and fixed stars revolving around it in complex, nested circular orbits. The model was wrong in its fundamentals, and yet it predicted the positions of planets with sufficient accuracy for practical use. Navigation, timekeeping, calendar making for over a millennium. The Ptolemaic model was transmitted to medieval Europe largely through Arabic translations, particularly through the work of Islamic scholars in Baghdad and Andalusia during the 9th through 13th centuries. Science is not a straight line from ignorance to knowledge. It is a long, meandering river that uses whatever channels the landscape of human circumstance provides. Islamic astronomy during the medieval period, roughly from the 8th century through the 15th, was not merely preservative. It was actively innovative, correcting and extending the Greek inheritance with new precision instruments, new mathematical techniques, and hundreds of new observations. Scholars such as al-Battani refined the measurement of the solar year and the precession of the equinoxes. Ibn al-Haytham wrote the first comprehensive treatise on optics, laying theoretical groundwork for the telescope that would follow centuries later. The names of many bright stars today remain Arabic in origin: Aldebaran, Algafalja, Betelgeuse, Fomalhaut, Rigel, Deneb, Altair, each name a small linguistic monument to the astronomers who catalogued and named them while Europe was otherwise occupied. Science crossed continents and centuries in manuscript form, each generation adding its careful corrections to the edge of what the previous generation had managed to see. Nicolaus Copernicus published his heliocentric model of the solar system in 1543, the year of his death, in a work titled Der Revolutionibus Orbium Coelestium, on the revolutions of the celestial spheres. His proposal that the Earth and the other planets orbit the Sun, not the reverse, was not immediately accepted, not least because a sun-centered model using perfectly circular orbits was, in practice, no more accurate in its predictions than the Ptolemaic model. The deeper revolution in understanding came with Johannes Kepler's discovery between 1609 and 1619 that planets move in ellipses rather than circles with the Sun at one focus, and that their orbital speeds vary precisely. A planet sweeps equal areas of its ellipse in equal times. These three laws, derived empirically from the extraordinary observational dataset of Tycho Brahe, transformed planetary astronomy from description into genuine dynamical understanding. The shape of orbits explained, for the first time, rather than merely recorded. When Galileo Galilei turned his telescope to the sky in 1609, he was not the first person to build such an instrument. The Dutch optician Hans Lippershey had invented it the previous year, but he was among the first to use it systematically for astronomical observation and to publish what he found. He saw craters on the moon, revealing a celestial body that was not the perfect smooth sphere Greek philosophy demanded. He observed 4 moons orbiting Jupiter, proving conclusively that not everything in the sky orbited the Earth. He saw the phases of Venus, consistent with Venus orbiting the Sun rather than the Earth. He resolved the Milky Way into innumerable individual stars. Each observation was a small, precise blow against a model of the universe that had held for 14 centuries. The telescope did not invent astronomy. It ended one kind of astronomy and forced another into existence. The discovery of the true nature of the Milky Way as a galaxy a disc-shaped system of billions of stars, of which our solar system is merely one small member, was not fully established until the early 20th century. For most of history, the Milky Way was simply the band of light across the sky, its nature uncertain. In 1785, William Herschel attempted the first systematic survey of the galaxy's shape by counting stars in different directions of the sky. But he incorrectly concluded the Sun was near the center, because dust in the galactic plane obscures the more distant regions in visible light. It was not until Henrietta Swan Leavitt's work on Cepheid variable stars in 1908, establishing a reliable method to measure stellar distances, and Edwin Hubble's application of it in the 1920s, that the true scale of the galaxy and our eccentric position within it were determined. Henrietta Swan Leavitt worked as a human computer at the Harvard College Observatory in the early 20th century, one of a group of women hired to catalogue and measure stellar brightnesses from photographic plates. In 1908 and 1912, she published her discovery of a precise relationship between the period of variation and the intrinsic luminosity of Cepheid variable stars. The longer a Cepheid cycle of brightening and dimming, the more intrinsically luminous it is. This period luminosity relationship meant that measuring a Cepheid's period and apparent brightness allowed astronomers to calculate its distance, the first reliable standard candle for cosmic distances. Without Leavitt's law, there is no Hubble constant, no confirmation that other galaxies are separate systems, no observational foundation for modern cosmology. She received no Nobel Prize. She died in 1921 before the full significance of her work was recognized, and Nobel Prizes are not awarded posthumously. Edwin Hubble's 1929 paper presenting evidence that galaxies are receding from us with velocities proportional to their distances, what we now call Hubble's law, was one of the most consequential publications in the history of science. By measuring the redshifts of dozens of galaxies, the stretching of their spectral lines toward longer, redder wavelengths caused by their recession, and combining that data with distance estimates from Cepheid variables, Hubble demonstrated that the universe is expanding. The implication is profound. Run the expansion backward in time, and everything converges toward a single point. The universe had a beginning. This was not a conclusion most physicists of the era were emotionally prepared for. Einstein himself had introduced a cosmological constant into his equations specifically to produce a static universe, and called it the greatest mistake of his life when the expansion was confirmed. The universe, it turned out, had never consulted anyone's preference for what it should be doing. The concept of the cosmic distance ladder, the layered system of overlapping measurement techniques that astronomers use to determine distances at increasing scales, is one of the great collaborative edifices of science, built across generations by hundreds of researchers, each tier depending on the tier below it. Parallax measurement works for nearby stars. Cepheid variables carry measurements to tens of millions of light years. Type Ia supernovae, with their consistent peak luminosity, carry the ladder to billions of light years. Each rung introduces its own uncertainties, which compound as the ladder extends further. The current mild disagreement between different methods of measuring the Hubble constant, known as the Hubble tension, may indicate a genuine gap in our understanding of the universe's expansion history, or may resolve with improved measurements. Either way, it is a reminder that the edges of the known always carry some negotiable uncertainty, and that this is not a failure of science, but its natural and productive condition. The concept of the cosmic distance ladder The layered system of overlapping measurement techniques that astronomers use to determine distances at increasing scales is one of the great collaborative edifices of science, built across generations by hundreds of researchers, each tier depending on the tier below it. Parallax measurement works for nearby stars. Cepheid variables carry measurements to tens of millions of light years. Type Ia supernovae, with their consistent peak luminosity, carry the ladder to billions of light years. Each rung introduces its own uncertainties, which compound as the ladder extends further. The current mild disagreement between different methods of measuring the Hubble constant, known as the Hubble tension, may indicate a genuine gap in our understanding of the universe's expansion history, or may resolve with improved measurements. Either way, it is a reminder that the edges of the known always carry some negotiable uncertainty, and that this is not a failure of science, but its natural and productive condition. The spectroscope, the instrument that spreads a star's light into its component wavelengths, producing a spectrum, transformed astronomy from a science of positions and motions into a science of physical nature. By examining the dark absorption lines that appear at specific wavelengths in a star spectrum, lines produced when particular elements in the star's atmosphere absorb the specific photon energies that correspond to their atomic electron transitions, astronomers can determine what a star is made of, how hot it is, how fast it is rotating, and whether it is moving toward or away from us. This technique, developed through the work of Fraunhofer, Kirchhoff, Bunsen, and others in the 19th century, revealed that stars are made of the same elements found on Earth, that the universe is chemically unified. Hydrogen and helium dominate the cosmos. The heavier elements are sprinkled in with increasing rarity. The stars are not foreign bodies. They are the same material at a different pressure and temperature. Vera Rubin, an American astronomer working in the 1960s and 1970s, measured the rotation curves of spiral galaxies, plotting how fast stars in a galaxy enter, and found something that Newtonian mechanics could not explain. Stars in the outer regions of galaxies rotate just as fast as stars near the center, rather than slowing down as expected from the visible mass distribution. This flatness of the rotation curve could only be explained if galaxies were surrounded by a vast invisible halo of additional mass that does not emit, absorb, or reflect light, and therefore cannot be observed directly. This was among the most compelling early evidence for what is now called dark matter, a substance that appears to account for approximately 27% of the universe's total energy density. Rubin never received a Nobel Prize for this discovery. She died in 2016. The dark matter she inferred has still never been directly detected. The term dark matter was not coined in the 20th century by Vera Rubin or Fritz Zwicky as a placeholder for ignorance. It was coined precisely because the evidence for its existence is overwhelming, even in the complete absence of direct detection. Dark matter does not emit light. It does not absorb light. It does not interact with electromagnetic radiation at any wavelength. It interacts with ordinary matter only through gravity and through gravitational lensing of background objects by galaxy clusters. The gravitational lensing of background objects by galaxy clusters, the large-scale structure of the cosmic web, and the precise temperature fluctuations in the cosmic microwave background all point independently to the same conclusion. The universe contains roughly 5 times as much dark matter as ordinary matter. The atoms, the stuff of stars, planets, oceans, and people, constitute only about 5% of the universe's total energy content. Everything we have ever seen or touched is the minority. Fritz Zwicky, a Swiss-American astronomer working at Caltech in the 1930s, was arguably the first person to identify compelling evidence for dark matter, though the full significance of his finding was not widely appreciated. For decades, studying the Coma Cluster, a large galaxy cluster, he measured the velocities of individual galaxies within the cluster and computed how much mass would be needed to keep the cluster gravitationally bound. The visible galaxies were nowhere near massive enough. The discrepancy was enormous. Zwicky concluded that the cluster must contain large amounts of Dunkel materie, dark matter, in quantities dwarfing the luminous material. He was largely dismissed or ignored at the time. Science, like any human endeavor, does not always recognize the important result the moment it arrives. Zwicky spent the rest of his career in a state of energetic and frequently acerbic frustration with the scientific establishment, a reputation that may have contributed to the underappreciation of his genuinely important work. The leading candidate particle for dark matter is called a weakly interacting massive particle, or WIMP. WIMPs are hypothetical particles that carry mass and interact with ordinary matter through the weak nuclear force and gravity, but are otherwise invisible to most detection methods. For decades, their theorized properties have made them extremely attractive candidates. Their predicted mass and interaction cross-section emerged independently from extensions of the standard model of particle physics, suggesting they might simultaneously explain dark matter and solve other theoretical puzzles. Enormous underground detectors, tanks of liquid xenon shielded from cosmic rays deep inside mountains or old mines, have been searching for the faint recoil that would result when a dark matter particle strikes an ordinary nucleus. So far, they have found nothing. The null results have placed increasingly stringent constraints on WIMP properties, and the most optimistic parameter space is narrowing. The particle remains hypothetical, the search continues, and the dark matter continues to hold its shape around every galaxy in the sky. Dark energy, the name given to whatever is causing the universe's expansion to accelerate, is even more mysterious than dark matter, because at least dark matter displays a consistent gravitational effect that its hypothetical constituents can be theorized around. Dark energy appears to be a property of space itself. It does not dilute as the universe expands, maintaining a constant energy density per unit volume even as the volume grows. This is precisely the behavior Einstein's cosmological constant, lambda, the term he added to his field equations and later called his greatest mistake, would produce. In the current standard model of cosmology, designated lambda CDM, dark energy is treated as a cosmological constant with a fixed value. But what that value is, why it has precisely the magnitude it does, and why it is not either zero or vastly larger, as naive quantum field theory calculations would suggest, is entirely unexplained. This discrepancy is sometimes called the worst prediction in the history of physics. The ultimate fate of the universe depends on the precise nature of dark energy and on quantities that current measurements cannot yet pin down with certainty. In the most widely accepted scenario, the lambda CDM model, the universe will continue expanding at an accelerating rate indefinitely. The lambda CDM model, the universe will continue expanding. Obdast de scenarios. The lambda CDM model descent at indefinitely rate indefinitely to sans. Galaxies beyond our local group will gradually recede faster than light can cross the space between us and eventually disappear from our observable horizon entirely. The cosmic web will thin, the voids will grow, star formation will eventually cease as galaxies exhaust their gas reservoirs. Over timescales of trillions to quadrillions of years, stars will burn out one by one, and the universe will grow dark. This scenario, sometimes called the heat death, or the big freeze, is not an explosion or a collapse. It is an extraordinarily slow dimming into a cold, vast, nearly featureless dark. Not a dramatic end, a very long, very quiet one. There is an alternative fate proposed by some cosmological models in which dark energy is not a constant but grows stronger over time. A scenario called phantom dark energy, or, at its most extreme, the Big Rip. In this scenario called phantom dark energy, or at its most extreme, the Big Rip. In this scenario called phantom dark energy, or at its most extreme, the Big Rip. In this scenario called phantom dark energy, or at its most extreme, the Big Rip. In this scenario, the energy driving expansion increases without limit, eventually overwhelming not just the gravity-binding galaxy clusters, then galaxies, then solar systems, but the electromagnetic forces binding atoms, and finally the strong nuclear force binding atomic nuclei, which tears apart in the final moments before the end. Every galaxy, every star, every planet, every molecule is ripped apart in rapid succession in the last seconds, minutes and hours of a universe that ultimately cannot hold itself together against its own interior repulsion. Current data slightly favor a cosmological constant rather than phantom dark energy, but the uncertainty is not yet small enough to rule out a Big Rip entirely. The universe's ending remains, at present, an open question. In the very deep future of even the lambda CDM scenario, after all ordinary stars have burned out, the universe will enter what cosmologists call the degenerate era, dominated by brown dwarfs, white dwarfs, neutron stars, and black holes. White dwarfs will slowly cool and fade over quadrillions of years, eventually becoming black dwarfs, cold, dark, inert carbon and oxygen spheres, though none are thought to exist yet, because the universe has not been old enough for any white dwarf to cool that completely, over even longer timescales, far beyond the current age of the universe. Protons may decay, if grand unified theories predict correctly, dissolving what remains of ordinary matter into radiation and leptons. After that, only black holes remain, themselves slowly evaporating through Hawking radiation over timescales so vast that the number of zeros required exceed the number of atoms in the observable universe. The last black hole blinks out. And then, a very, very long time of heat-death silence. The Big Bang itself was not an explosion in the conventional sense. It was not an event in space. It was the event of space. The Big Bang describes the very rapid expansion of an extraordinary hot, dense state of the early universe. Not matter exploding outward into pre-existing empty space, but the emergence of space, time, matter, and energy together from a state in which all four were unified and effectively without independent meaning. The earliest moment from which current physics can derive reliable descriptions, the Planck epoch, less than 10 after the beginning, the earliest effect, less than 10, remains beyond the reach of any current theory, because both quantum mechanics and general relativity are needed simultaneously at those scales, and the two theories are not yet unified into a single coherent framework. What preceded the Big Bang, or whether preceded is even a meaningful concept when time itself began at that moment. These are questions that physics has not yet answered, and may never answer from within the universe the Big Bang produced. Cosmic inflation, a period of extraordinary rapid exponential expansion thought to have occurred in the first tiny fraction of a second after the Big Bang, is the leading explanation for several key features of the observable universe. Why it is so flat? Its overall geometry appears Euclidean to extraordinary precision. Why it appears uniform in temperature everywhere across the sky. The cosmic microwave background varies by only 1 part in 100,000. And why it contains the specific pattern of density fluctuations that seeded all the structure we see today. Inflation would have stretched any initial curvature to flatness and homogenized temperatures by rapidly expanding a tiny, initially well-mixed region to encompass the entire observable universe. The theory was proposed by Alan Guth in 1980. It makes predictions that have been confirmed by multiple independent CMB surveys. But the specific inflationary mechanism remains undetermined. There are dozens of candidate models, and distinguishing between them awaits future precision measurements. One of the most haunting implications of an accelerating, ever-expanding universe is the growing isolation of our cosmic neighborhood. Right now, the observable universe contains roughly 2 trillion galaxies. But as expansion continues and distant galaxies cross the cosmic horizon, receding faster than light can chase them, the number of galaxies permanently accessible to any future observer grows smaller. In 100 billion years or so, the local group will have merged into a single large elliptical galaxy. Milkomeda and all other galaxies will have long since disappeared beyond the cosmological horizon, invisible and unreachable. Any civilization born in that far future epoch, if the universe still permits civilization, will see only a single galaxy in an otherwise apparently empty universe, with no light from beyond to hint at the vast cosmic web that once existed. They would have no empirical access to evidence of the Big Bang, no way to measure cosmic expansion, no way to know what we know. The window on the universe is open now. It is slowly, inexorably closing. The multiverse, the hypothesis that our observable universe is merely one of a vast or infinite ensemble of separate universes, is a concept that emerges naturally from several distinct areas of theoretical physics, including eternal inflation, string theory's landscape of possible vacuum states, and the many worlds interpretation of quantum mechanics. In the eternal inflation framework, the rapid inflationary expansion that preceded our Big Bang may never have fully stopped. Only our local region of it did, forming what we experience as the universe. Other regions, still inflating, would produce their own separate bubble universes, with potentially different physical constants, different laws, or different dimensions. The multiverse is, at present, scientifically controversial because it may be fundamentally untestable. If other universes are truly causally disconnected from ours, no observation within our universe can confirm or deny their existence. It sits at the precise boundary between cosmology and philosophy, which is a boundary the universe appears not to recognize. The question of whether the laws of physics are the same everywhere in the universe, whether the fundamental constants are truly constant, is one that observational cosmology takes seriously and can, in principle, test. The fine structure constant, which governs the strength of electromagnetic interactions, has been measured using the spectral lines of quasars at great distances and great cosmic ages. Some studies have reported subtle hints of variation across cosmic directions, suggestive of a spatial gradient in the constant's value, though these results remain contested and unconfirmed by independent measurements. If fundamental constants do vary across the universe, the implications would be profound. The chemistry of life, the stability of atoms, the properties of stars, all depend sensitively on the specific values of these constants. A different fine structure constant elsewhere might mean a universe where atoms cannot form, stars cannot burn, and the particular narrative of complexity that led to living things asking these questions would simply not arise. The anthropic principle. The observation that the universe we observe must be compatible with the existence of observers, since we are here to observe it, is a tautology that nevertheless carries genuine explanatory weight in the context of cosmological fine-tuning. The universe's physical constants appear to be set within extraordinarily narrow ranges compatible with the existence of complex matter, chemistry, and life. Slightly stronger gravity, and the universe would have collapsed before stars could form. Slightly weaker, and matter would never have gathered into galaxies at all. The strong nuclear force within a percentage point of its actual value and stable nuclei could not exist, and neither could chemistry. Whether this fine-tuning reflects intelligent design, the selection effect of the multiverse, or simply the bare fact that in any universe where the constants were otherwise we would not be here to measure them, is a question that physics alone cannot answer. It is the point where the instrument of science reaches its outer edge and hands the question onward, quietly, to something else. The moon is not merely Earth's companion. It is one of the primary reasons Earth is the kind of planet it is. The moon stabilizes Earth's axial tilt to within a range of roughly 22 to 24 degrees over tens of thousands of years, preventing the extreme wobbles that a moonless Earth would undergo. Swings of planetary tilt that could dramatically destabilize climate over geological timescales. It also slows Earth's rotation through tidal friction. Early in Earth's history, a day lasted only 6 hours. The moon's gravitational braking has gradually lengthened it to 24. The tides themselves, driven by the moon's gravitational differential across Earth's diameter, the chemistry of early coastal environments, creating the rhythmically wet and dry zones that some researchers believe were crucial incubators for the development of complex organic molecules in the oceans of the young Earth. Saturn's rings are among the most visually extraordinary structures in the solar system, and among the most temporary. Despite their apparent permanence and their iconic status in every image of the outer solar system, the rings are thought to be geologically young, perhaps only 100 million years old, formed well after the age of the dinosaurs had already begun on Earth. And they are actively disappearing. Ring rain, the process by which charged water particles from the rings are drawn down Saturn's magnetic field lines into its upper atmosphere, is removing ring material at a rate that would completely eliminate them within, perhaps 100 million years. We happen to exist in the narrow window of time during which Saturn has rings substantial enough to see. A few 100 million years earlier or later, and a visitor to this solar system would find Saturn unremarkable, just another ringed planet in the process of losing what made it beautiful. Jupiter functions as a gravitational shield for the inner solar system, deflecting or capturing many of the comets and asteroids that would otherwise threaten the terrestrial planets on shorter timescales. Its enormous mass, more than twice that of all other planets combined, means its gravity well intercepts a disproportionate fraction of incoming small bodies from the outer solar system and the Kuiper Belt. The 1994 impact of comet Shoemaker-Levy 9, which Jupiter's tidal forces had already torn into 21 separate fragments before they struck, left temporary dark scars in Jupiter's atmosphere larger than the diameter of Earth, and offered a sobering demonstration of what such an impact would mean for a terrestrial world. The question of how much Jupiter's shield effect has benefited life on Earth. by reducing large impact rates to a frequency that biological complexity could survive, remains genuinely debated, but the geometry of the solar system suggests the benefit is real. On February 14, 1990, as Voyager 1 was leaving the solar system, astronomer Carl Sagan persuaded NASA to turn the spacecraft's camera back toward the inner solar system one final time. In the resulting image, Earth appeared as a pale blue dot, less than a pixel in size, suspended in a beam of scattered sunlight against the black of space. Sagan reflected on that image in words that have since become some of the most widely quoted in science, that on that point of light every human being who ever lived had lived out their lives, that all the rivers of blood spilled in the name of conquest and superiority were for a mote of dust, suspended in a sunbeam. The pale blue dot image is not primarily an astronomical achievement. It is a philosophical one, a portrait of context assembled from a distance of about 6 billion kilometers, looking back at everything that has ever mattered to anything that has ever been capable of mattering. The search for extraterrestrial intelligence, SETI, has been ongoing in various organized forms since 1960, when astronomer Frank Drake pointed a radio telescope at two nearby sun-like stars and listened for artificially structured signals. More than 6 decades of systematic sky searches have produced no confirmed detection, though the search has intensified enormously in scope and sophistication. The Breakthrough Listen initiative, launched in 2015 with substantial private funding, is the most comprehensive SETI program ever conducted, monitoring millions of stars across multiple frequency bands with extraordinary sensitivity. The absence of a confirmed signal does not mean absence of signal. Most of the sky has been searched only briefly, at limited frequencies with instruments that may be poorly matched to whatever communication methods a technological civilization might actually use. The search is still very young relative to the depths it is trying to probe. Silence is not yet a conclusion. It is still a question, held open and patient. The Drake equation, formulated by Frank Drake in 1961, as a framework for estimating the number of communicating civilizations in the Milky Way at any given time, is less a calculation than it is a structured articulation of ignorance. It multiplies together several biological flavors, astronomical and cultural factors, the rate of star formation, the fraction of stars with planets, the fraction of those planets capable of supporting life, the fraction where life actually develops, the fraction that develops technology, and the average lifespan of such civilizations, to produce an estimate that can range from less than 1 to many millions, depending on the values chosen. Most of the factors remain poorly constrained. What the equation has done magnificently is to organize the question, to transform, are we alone, from an unanswerable philosophical musing into a set of specific scientific sub-questions that can in principle be investigated and narrowed one by one as observation improves. The Fermi paradox, named for physicist Enrico Fermi's offhand question at a 1950 lunch, "But where is everybody?" distills a genuine tension in our understanding of the cosmos. If the universe is as old and as vast as it appears, and if life and intelligence arise with any reasonable frequency, then some civilizations should have had billions of years more than ours to develop and spread through the galaxy. Even at a fraction of the speed of light, a civilization expanding steadily outward could colonize the entire Milky Way within tens of millions of years, a geological eye blink in cosmic time. And yet there is no sign of them, no signals, no megastructures, no unambiguous evidence of any kind. The explanations range from sobering to terrifying. Perhaps life is extraordinarily rare. despite the right conditions. Perhaps civilizations reliably self-destruct before they can expand. Perhaps we simply have not looked long or carefully enough. Or perhaps the silence is simply what the beginning of the story sounds like. In October 2017, astronomers detected an object passing through the inner solar system on a trajectory that was unmistakably hyperbolic, meaning it had not arrived from any orbit bound to the Sun, but had entered from interstellar space, the first confirmed interstellar visitor ever observed passing through our solar system, named Oumuamua, from the Hawaiian for scout or messenger from afar. Arriving first, it was acceleration observed in its outbound trajectory, beyond what solar radiation pressure alone should produce, that made it truly strange. Several mundane explanations have been proposed: outgassing, radiation pressure on an unusually flat, thin geometry, but none have been universally accepted. Astronomer Avi Loeb proposed, controversially, that Oumuamua might be an artifact of non-natural origin. No consensus has reached that position, and Oumuamua is long gone, now irretrievable, departing the solar system on its interstellar trajectory before any detailed study could reach it. Whatever it was, it came from somewhere else, and was only passing through. The atoms that make up your body are not new. The hydrogen in your blood plasma formed in the first 3 minutes after the Big Bang. The carbon in your DNA was synthesized in the cores of stars between 1 and 10 times the mass of the Sun, in the final stages of their lives, through a nuclear reaction called the triple alpha process, before being scattered into the interstellar medium by stellar winds and supernovae. The iron in your hemoglobin was forged in the cores of massive stars and released when they exploded. You are, in the most literal and non-metaphorical sense possible, made of the debris of dead stars. The residue of nuclear processes that occurred billions of years before the Earth existed, carried through space in the expanding shells of stellar explosions, gathered by gravity into the cloud that became our solar system, built by chemistry into the molecules of life, and organized by evolution into the particular arrangement of matter that is right now, growing quietly still in the dark, listening to the universe describe itself. And so the 100th door closes, not with finality, but with the same quiet it always had. The universe has been speaking tonight in the only way it knows, through the evidence it leaves in the light that traveled to reach you, in the dark that holds its shape, in the atoms you carry from stellar explosions older than the Sun. You did not travel to the cosmos tonight. The cosmos traveled to you, as it always does, as it has always done, in every particle of everything you are. Times. You have listened well. Now sleep.